Alrighty. Welcome. So welcome back. Um, this is introduction to decision trees, ensemble method, and bootstrapping. I'll be your host for the day, but as I used to say, we're here to learn, so I'll also be keen to learn from all of you. So please participate as we dive in. All right. As always, you know the rules of engagement. If you have any questions, please post them on the Q&A section. Feel free to use the chat liberally and respectfully. Most importantly, you should listen, learn, and engage. Now, before we dive in, can you recall any childhood memories that make you happy? I will tell you my own, but after I hear yours. So can you do that in the chat? Any takers? Nobody is responding. I don't want to be the only one responding. But anyways, can you all hear me? Please let me know whether I'm on the chat. On the call. Okay. Sheko is saying not worrying about providing for yourself. Yes, this is interesting because as a kid, you don't care whether you don't care where the next salary is coming from or the next income. All you care about is just see the food on the table. And kids, sometimes they can be funny. Like sometimes you can present them a variety of food, they will tell you they don't want that. So yes, like you don't care, just you're just waiting for the problem to be solved. No worries. When you are not feeling well, it's your parents. I'll just take care of that. So God bless our parents. Oliver is saying, my long lost friend, I can't remember her. And that's interesting. That's interesting. Then Kenya is saying, I remember my first time going go karting. Okay. So what is karting? Alex is saying, when I rode my first bicycle. That's interesting. That's interesting. Michael is saying we used to go steal plants, either maize or sweet potatoes, burn them, roast them, and then we eat. Fishing, roasting, and fish to eat. Those are nice childhood memories. Christine is saying new clothes for Christmas Day. Mm. Ushira is saying not caring about food provided now. I'm done planning what other people will eat. I miss those days. That's one interesting paradox or one interesting irony about human life. Like the young, we want to be old to see what the old life is. And when somebody is old, he will not think, why can't he go back to being young? Like somebody that is famous, all of a sudden he will say he like privacy. But somebody that is not famous will say he like fame. So that's that about that. Now, however, before we dive in, I have this one video that I want to play for you. So please watch and tell me the message you learn from the video. All right.
Good morning, school. Now, there are students here who are not disciplined. And I'm going to call you, I have the list here, and I'm going to call you out for your punishment.
Yes, Bridget.
If you know you are not in the right school uniform, come in front and kneel down here. Quickly. Kneel down here. Kneel down and face them. Now, second category, if you know you are supposed to sweep and you didn't sweep, I have your names here. Number one, Christina Chien. Where's Christina Chien? Come here. Kneel down here. Number two, Sajon Ochien. Where's Sajon Ochien? Come here. And you're laughing. You're laughing and you're going to be killed. And the last one, Bridget Bema. Okay? Mother tongue speakers. Asin Ochien. Kneel down here. Jevins Marvel. Kneel down here. Bridget Bema. Latecomers. Lois Anyango. Where are you? Where's Lois Anyango? Lois Anyango, come here. Kneel down here. Evans Onyango. Where's Evans Onyango? Kneel down here. And again, Bridget Bema. Noise makers. ALX Otieno. Come here. Kneel down here. Malia Tracy. You're making noise. I don't believe you. Bridget Bema. Again. Aya, bullies. Those who like bullying other pupils in class. Candelaria, where are you? You're the one. Go and kneel down there quickly. You are bullying fellow pupils. Kneel down there. We have got Sheridan Lindsay. Where's Sheridan? You are bullying fellow pupils. Go and kneel down there. The last one we hear is Bridget Bema. Bridget Bema. And we have students who don't obey teachers. There is one student there who, whatever the teachers tell them, they don't obey. Bridget Bema. And you're smiling. Come here.
All right. All right. So, if you are the teacher, what are you going to do to Bridget, the legendary Bridget Bema? And let me know in the chat. Oh, yes, that's Bridget. All right. What are you going to do to her? All right, so that notwithstanding, why am I bringing this video? Why am I bringing this video? Because this is similar to what we are going to discuss today. That's decision trees, right? So decision trees, just like the way the teacher is having a lot of students. So those lot of students, each one of them can represent a data point, like one row on your data set, right? Now, you may decide to like classify the students. So at every point of doing the classification, you will ask for one criteria. Who meets this criteria? Then those that meet the criteria will go to one side. Those that didn't meet the criteria will go the other side. So we can see in the first criteria, Bridget was on the other side, the remaining students were on the other side. So then the second criteria was used, but fortunately for Bridget, she also made the second list and continuously like that. So that is similar to what is happening with decision trees. At each node, a question is asked. Those that meet the question will go to the one side. Those that didn't meet the question or the criteria will go to the other side. Yes, Idowon is saying as a teacher, she needs some counseling. Yes, exactly. All right. So for today's discussion, we want to understand decision trees and ensemble methods. And not only that, we should be able to apply decision trees in building projects. Right, let's dive in. Decision tree works by splitting data into subsets based on the value of input features, creating a tree-like structure of decisions, right? So a decision tree is one tree where the normal tree that we know is supposed to be upright, meaning the root is on the ground or is penetrating the soil, whereas the branches are at the top. However, this kind of tree is weird in the sense that it is upside down. So the root is at the top, which is called the root node. So this is the root node. It's at the top. Then, and that's the root of the tree. Then we have the stem of the tree. So these lines, they are the stems. Then we have the branches. So this is a branch. All right. So after the branch, what next? We have the node or the leaf. So first of all, we have another node here, which is decision node. And at the tail end, we have the leaf node. All right, so here is the leaf node. So this is our leaf node. And so what happens? At each of these nodes, a decision will be made. And the decision will be based on a certain criteria. So suppose you are having, or let me not preempt that, but if you look at this, this is a subtree, meaning if you cut off this, it can stand as a tree on its own, right? All right, so next, okay, next we can, this? Next we can go to, we can have a concrete example. So suppose, let me ask this question before the example. What do you think can affect heart health? What do you think can affect heart health? So let me know in the chat. Okay, well, Deborah said smoking. So smokers, please try as much as possible to stop smoking because it can affect your heart. Blood clots. Okay. Alcoholism. Fats. Exactly. Too much oil. Kidney failure. I think you are getting it. So, in essence, this is a typical example of where we want to categorize whether somebody is at high risk of getting heart disease or at low risk of getting heart disease, right? Now, to do that, what are we going to look at? First of all, we look at the age, because the common rule of thumb is the older you are, the more likely you are to fall. I mean, you are at higher risk of getting cardiac issues when you are old, right? That is one. Then the weight also. So just like somebody was saying, fat. So the more weight you gather, the more likely for someone to develop health issues. Then smoking, as somebody also indicated, right? These are not the only ones, but for the purpose of this demo, we are just taking this. So first of all, like when you have a data set about so many patients, like let's say 10 patients, then all of those patients, for each one of them, maybe you collect his name, his age, then his smoking habits, and then maybe you measure his weight and even sometimes his height in order to calculate the BMI. Now, uh, after you collect all these uh, attributes about a given patient, then you now want to categorize the patient into those that are more likely to or more susceptible to cardiac issues, and those that are less likely to have that cardiac issues or those cardiac issues. Now, first of all, you may say, okay, to categorize this patient, let me use age as my first criteria. So you ask the question, are you less than 18 years? If the answer is yes, then go my left. All right, so then after you go to the left, the next question that may be asked is, that's the next thing that you may use to differentiate the patient. You can use age again, or you can use another criteria. So for example, you may use the weight as the second criteria. Then you say, is your weight less than 60 kilogram? If yes, then maybe the patient is at low risk of developing heart issues. However, if the person is less than 18 years, but he is heavy, like 60 kg, then it means he's at high risk of developing cardiac issues. All right, so at the end of the day, this is classified as either low risk or high risk based on the answer that we get. Then maybe the next question is the person between the age of 18 and the age of 30? If yes, and maybe that's only age that we use as a criteria, then we may say he's at low risk of developing heart attack or heart issues. All right, then the next one is, is the person greater than 30 years? If yes, okay, is he a smoker? If no, then he may be at low risk. If yes, then he may be at high risk. So as I was saying, this is also a subtree, right? So based on this, we are able to classify the different patients. Although in this session, we are only going to discuss regression, not classification, but this decision tree is also useful in both regression and classification, and I found out that the explanation for classification is more coherent than that of regression. So that's why I'm using the classification instance instead of that of regression. All right. And I don't know, does that make sense? Or do I need to go over? All right, thank you for responding. Now, having said this, somebody may be asking, so what informed the criteria? So if you are as a human, you may use your own criteria arbitrarily, right? But in the case of machine, there is a guiding principle that inform the choice of the criteria. So what the machine will do at the initial iteration of the problem, it will do some calculation for for all the features, for all the columns. Then it will check which one is having the highest Gini index. If Gini index is the criteria that we want to use, so it will ask the question out of all these features, which one should I use as a criteria to split the data set so that I'm having the highest Gini index? So this Gini index is like the information index. That's the amount of information that is contained based on that split. So the more the information, the better the results. And in some instances, it may be that MSC might be the criteria that you may use in order to choose to split the columns, right? So maybe you have 4 columns like name, gender, age, what again? Maybe geographical location. So maybe you have these 4. So which criteria are you going to use? Then you will ask yourself, okay, if I use gender, will my MSC be small? Or is my MSC going to be the smallest? If yes, then gender will now be used as the criteria for splitting your data sets. So then that's at the initial stage. Then at the next stage also, another Gini index will now be evaluated, and it is going to be used to compute who is going to where and the rest of that. So that's how it continues until you reach the final leaf where decision is made. All right, so then next up, we have the ensemble methods. So this ensemble method, we all know that they used to say 2 heads are better than 1, right? Although we are meant to understand that it is 2 good heads that are better than 1 good head. So you may have a situation whereby 1 good head is even better than 10 bad heads. So, but what we are just trying to say is, whenever you have 2 good heads, then they are better than 1. So that's the wisdom being employed in ensemble methods. So instead of just having like one model doing the classification or the regression, multiple models, one goal. That's to make prediction. So ensemble methods combine predictions from multiple models, often called the weak learners or base models, to produce a final prediction that is generally more robust and more accurate and reliable than any individual model. Just like similar to saying none of us is better than all of us. The methods are classified into homogeneous and heterogeneous methods. So what do we mean by homogeneous? So in the case of homogeneous, all the models are the same. In the case of heterogeneous, the models are not the same, right? So it's just like when you are forming a team, when you are forming your tech team. So maybe if you choose all the team members from Rwanda, then that may be regarded as homogeneous team. But if you say, okay, let your team members be from various African countries like Zimbabwe, Cameroon, Ghana, Togo, then in that case, we may say you are having heterogeneous team. So that is also what is employed in ensemble method. When all of them are similar, we call them homogeneous. When they are different, we call them heterogeneous. Then this homogeneous is of different types. One of the types is called bagging. So the homogeneous ensemble method, one of that is called bagging. It combines predictions in parallel from identical models trained on different bootstrap sample with replacements. So what do you mean by this? Suppose you have a record of 10 individuals. So in bagging, what they do is like they say they sample, right? So by sampling, maybe you are just picking like 4 or 6 out of the 10. So when you pick 6 out of the 10, then maybe you train them on a model like decision tree. Then along the line, you also have another decision tree that will randomly sample the same 10 rows, but it will randomly sample them, maybe pick another 6, which is not the same as the previous 6. All right. So you may have the third one also sampling based on that. So the different subsets are now going to be aggregated, right? So subset of data to reduce variance and prevent overfitting. Why are we doing this? In order to reduce the variance and prevent overfitting. Another one is called boosting. So boosting is a sequential ensemble method where each model focuses on correcting the errors of its predecessors, So how I wish African leaders will just focus on correcting the errors of their predecessors. Because no matter what you say or what you do, you must make mistakes. So if you make mistakes, like when a leader is succeeding you, he should not emphasize on those mistakes, rather try to see how to correct those mistakes and also try to make less mistakes. And that is how the country will progress, right? So, but when you focus your energy on criticizing the previous administration, you will not have time to do your own work. So maybe the criticism that you are even doing, that's also part of your own mistake. So it's better you just focus on correcting the mistakes of the past so that you can move ahead. You too, you will also definitely make mistakes. So somebody will correct your mistakes later on. So why are we correcting the previous mistakes? Like aiming to reduce bias and build a strong predictor from weak learners. So that is boosting. So you can even hear the word boosting, like one will enforce the other. Then we have stacking. So this stacking is a heterogeneous method. So in stacking base models are trained on the original data, and their predictions are used as input features for the meta model, which produce the final prediction. Then we also have voting. I know you all vote, right? So similar, in voting, they say majority carry the vote. So that's also what is happening here. After each individual model have done its own part, its own prediction, the error metric will be calculated, or the evaluation metric will be evaluated. Then those ones with the least errors, they now carry the vote, right? That's in the case of classification. If it is in the case of regression, they take the average of the final prediction. All right, does that make sense before we change? All right, thank you very much for confirming. Now we can move ahead. All right. So I've already explained this. This is root node. These are the internal node. These are the leaf nodes. Okay, just to add some English to what you are seeing. Here we have node. Each internal node of the tree represents a feature or attribute of the data set. So attribute like age, weight, height, all these ones are attributes. So each node is representing one of the attributes. The decision made at this node determines how the data will be split. Edges. The edges or branches represent the outcome of the decision made at the node, right? So what comes out of here, either yes or no. So these are the edges. Then we have the leaves. The leaf nodes represent the final output or prediction. So this is the final output. So if it is classification, this will be classes. If it is regression, this will be numbers. And they also serve as the final predictions. Then what again do we have? We also have the depth of the tree. So what do we mean by the depth of the trees? If you take any tree, the longest branch, that's the depth of the tree. So this depth of the tree is very important. For example, if you build a tree that is so deep, what do you think will happen if you build a tree that is so deep? Meaning you have a tree that is having a lot of branches. What do you think will happen? Oh, somebody say low sound. Do I need to like increase my voice? Alex Walker is saying low sound. Do I need to increase my voice, or can you all hear? Alex, can you hear me now? Okay, thank you. Okay, thank you. So I think for the purpose of Alex, maybe I will need more energy in order to to say what I want to say. Okay, just I hope I can I can speak louder than this. Okay, so what do you think will happen when the okay, Kanya is saying the tree will eventually split. Well, the tree has been splitting right from time immemorial. All right, so splitting is the is the function of the tree. All right, so what happens is if you dig if you build the tree that is so deep, then you risk overfitting, right? Overfitting is like, okay, let me just show you overfitting on a diagram. All right, so what do we mean by overfitting? For example, this is overfitting, right? Like the model is trying to follow all the points, all of them. So the problem is when your model is behaving like this. Now, if you pick a sample from the training set, the model will perform wonderfully, magnificently, right? However, the moment you try to test the model on unseen data, it will perform woefully. The performance will be very poor. So this is also another case of underfitting. So in the case of underfitting, you can see the model is oversimplifying the data. So you can see this line, this dotted line, that's the model we're talking about. So this point, each one point here is a data point. All right. So when you just say, when your data set is like this, and you just go and fit a straight line on it, definitely you are not doing justice to the data. So the straight line is not representing most of them. So maybe a line that will represent this is parabola, that's x square, right? So, but if you go and put a straight line, then that is underfitting. But if you say you want to place all the lines, you can create a function that will pass almost all the points. However, when you do that, then you have overfitting. So the essence is to have something that is like balance between overfitting and underfitting. So like this good fit or robust, maybe when you fit a parabola, then this is more representative than all of them. All right, so when you go and put the depth of the tree to be like 100, you risk overfitting the data. All right. So Alex, apologies if the sound is still not loud. Maybe you can try other devices, one, or I don't know whether watching the recording will also be louder than this, but it's something that you can also try. All right. Apologies for that. So now for a given decision tree, we see the nodes, the edges, the leaves, the depth of the tree. So how is decision made? I think I've already explained this. First of all, we start with splitting. So we start with splitting. Then after that, we do recursive partitioning. So what do we mean by recursive partitioning? Meaning this partitioning will keep going. Okay, so just to buttress a point, who can tell me what is the depth of this tree? on the screen. Can somebody try? What's the depth of the tree on the screen? Just by the way, the number of nodes determine the number of tree. That's the number of nodes on a path, not all nodes, but the number of nodes on a given path, or the longest path, that determines the depth of the tree. So what is the depth of this tree? Can anybody help us? Interesting. Somebody said 3. All right. Anyone? Oh, our tree is having 3 as the depth. All right. So usually when you come, this root node, you count it as 0. So this is 1, this is 2. So we say the depth of this tree is 2. All right. So here, we do recursive partitioning, meaning we keep building branches and nodes. After that, until when are we going to stop building the branches? Maximum depth of the tree is reached. Meaning, if the depth of the tree is 2, you reach 2, so you stop. Or a minimum number of samples in a node is reached. So maybe you want the minimum number of samples in a given node, like this leaf node. You want the minimum number of samples, meaning for example, if you are having a data set about patients, so the minimum number of patients you want to have on any of this, maybe if you want 5. So the moment 5 is reached, then everything will terminate. Even when this is 10, this is 30, this is 40. If this one is 5, everything will just stop. Then no further improvement can be made in the split. So maybe this is a situation whereby the model itself thinks that no any further improvement can be made, then it will terminate the splitting. Then we say prediction. Once the tree is built, predictions can be made by traversing the tree from the root to a leaf node based on the feature values of the input data. All right. What are the advantages of decision trees? One is interpretability, meaning you can easily interpret what the data is doing. Like there's a way you can generate this tree after you finish modeling your data. Though sometimes if the data set is very large, then it's going to take a lot of time before this structure is generated, but it's something that you can generate. No need of feature scaling. So, in our previous exercises, we do scale the features. So in the case of decision tree, you don't need to scale anything. Then handling nonlinear relationship is natural. One disadvantage is overfitting, just like we finish discussing. Another one is instability, meaning small change in data can lead to wonderful changes in the outcome. Bias toward features with more levels. So if you have feature sets where maybe you have a feature with like 100 levels, meaning 100 different values, compare it to another feature that is maybe having only 2 values, then in that case, the model may be biased towards those features that are having 100 levels compared to those with 2 levels. So which project are we going to work on? Predicting the New York City taxi trip duration using decision trees. Now, what is the business context? I see somebody is laughing. Is it because the cab is yellow? I don't know. By the way, why is it that taxis are all yellow? Most of them are all yellows. Does anyone have any explanation? So the business context. Oh, Jeff is saying the car is too good to be a taxi. Well, uh, I think maybe in our countries, in some of African countries, it may be too good to be a taxi, but maybe in some other countries, it's normal to have a taxi like this. Right. So the goal is to predict trip duration in seconds for taxi rides based on trip details such as the pick-up location, the drop-off location, the time, maybe the number of passengers. Well, can the number of passengers determine how long the duration is going to last? Accurate trip duration or prediction. So this trip duration, can somebody tell me why is it important for us to know or to predict trip duration of a taxi? Oh, Daniel is saying easy identification since yellow is a bright color. Yes, that's fantastic. I think that's one of the main reasons why. Yes, Busiswe is saying easy to see from far away. Yeah, you are all correct. So now, why is it important for us to evaluate trip duration? Any takers? Okay. Okay, I can see one. Kaya is saying to calculate rate per kilometer, perhaps. Thank you for trying for the attempt. So any other one? All right. So what is the economic value of knowing the trip duration? One, we are going to improve ride-hailing efficiency. Busiswe is saying pricing prediction. Yes, thank you for that. Yes, if you want to predict the price, so sometimes you can use the duration it takes for you to cover that distance. Another one is optimize driver allocation. So, for example, if you have a ride-hailing app like Uber or Bolt, in that case, Uber used to like distribute their drivers what is it called? Based on places with high density of passengers, right? So based on that, that's how Uber distribute their drivers. So how do you efficiently distribute the drivers? The trip duration can help you achieve that. Another one is it provides better ETA for users. So you as a user, I don't know how many of you have used Google Map to locate a certain point or a given address. And if, okay, how many of you have done that? Yes, Kaya is saying high traffic zones, exactly. So, for example, in the case of, yes, thank you for confirming. And now sometimes when you want to, most especially if you are traveling on your car from one place to another, and maybe you don't know the place. So you can just put the address of the place on your Google map, and then you start navigating. Then immediately you start navigating, Google Map will calculate the expected Google Map will calculate the expected time of arrival, and sometimes it will give you like plus or minus 5 minutes. How is Google Map trying achieving that? Maybe sometimes as you are speeding, you see that the Google Map will be measuring your speed, right? So when you check the speed on your Google Map, you see that it is coinciding with the speed on the speedometer of the car. So it will use that, and based on the distance, it will be able to tell you that, okay, this is your expected time of arrival. So how can Google provide better estimates to users? You can use this trip duration to achieve that. All right, so which data set are we going to use for today's discussion? It is a data set about the New York City taxi trip duration, and it is having features like the pick up, drop off, coordinate, timestamps, passenger count, and vendor information. All right, then here we are going to import the necessary libraries. Now, having imported the necessary libraries, so this is a data set that I got from Kaggle, and the data set is heavy. So you can also get it from Kaggle, that is one. However, I will compress it and shift it along with the notebook for your own perusal. So here, what I did, I upload the data on my Google Drive. So because of that, I need whenever I want to load the data from my Google Drive, first of all, what I will say is from google.colab import drive. Then I will need to mount the drive before I can be able to access the data. Now, when you get this notebook, you can run the notebook locally on your Jupyter notebook, or so in that case, you don't need this. All right. The only thing you need is to pass the path that's in your notebook, which is here. However, if you also upload it in your in your Google Drive, so you need to run this cell. Yes, connect to Google Drive. All right, so as it is connecting, then next up, now it is mounted. Now we can do our pd.readcsv. So this is the path to the data set. So how do you copy the path? You can click this folder icon, then open Drive, My Drive. So for me, I put it inside webinar prep. So under webinar prep, this is the, where is it? Okay, this is the New York City trend.csv. So if you are downloading it from Kaggle, take note on Kaggle, because this is a computation. So this is also something that I would like you to try to compare yourself based on what other people are submitting. So when you get this notebook and you do your modifications, please try to submit on Kaggle to see your score, because the competition is open. It is open-ended. You can submit at any given time and you get your grades. So, and normally what they do in Kaggle, they will give you the training set, which is separate from the test set. So the test set, they expect you to use it to submit your own entries or your own submission. So what I did, normally the test set is not going to have the target. It is only going to be features. So they expect you to use the model that you create to generate the targets. So those targets will now form the prediction, and you can then submit the prediction and get your grades. So here you say copy path, and after that you come here and you paste the path. So when you do that, you can run this. So this data set is very heavy, but all right, it is loaded now. So after we finish loading this, the next natural thing to do is what? We say df.head. Just to have a sense or a glimpse into the data set. So we can see here we have ID, we have vendor ID, we have pick up date, we have drop off date, time, we have passenger count, we have pick up longitude, pick up latitude, down to the trip duration, right? So we want to predict this trip duration. I remember we are told that this trip duration is in seconds. All right. Store and forward flag, okay. So all these are what? Are in our data. So can somebody help us? What next should we do? What next should we check? Can somebody help us with the next code? Oh, Philomena is saying the sound on my side, there's a lot of echoes. Okay, I don't know why I'm having echoes. Okay, let me turn off this computer. Whether it is the one affecting it. I had df.shape. Thank you very much. So we may also say df.shape and so that, oh, what is happening? Oh, this is attribute, so we don't need the parentheses. All right, so how many rows can we see from here? Let me see somebody with sharp eye. Is this 14,000, 145,000 or what? Is it in the range of thousands, hundreds of thousands, or millions? Yes, 1 million. So our record is we're having 1.4 million. Thank you, Kevin. Thank you, Ido. Thank you, everyone. And the number of columns is 11. Okay. So next up, what next? After DF shape, somebody is saying we should check the null values in the data set. Yes, thank you very much. We will do that. But what next can we do? df.describe, right? Thank you very much. So we say df.describe. Right, but before df.describe, there's also df.info. Right. All right, so here we can even see that we are seeing the shape, which is this is the number of entries, which is 1.4 million. And we can see the memory is up to 122 megabytes. Then somebody is asking, we should look for null values. So looking at this is non-null. So all these ones, they are non-null. And we can see none of them is less than this. So because none of this is less than this, we can safely say that there is no null values, right? And but there is also another function that you can use to evaluate that. So for example, if we say df dot is null, so we can see what this is returning, which you may not be able to fathom what is happening. So what else can you add? You can say sum. Maybe just try to count everything. So you can see in all the columns, none of them is null. So the number of nulls are all zeros. All right, then the next thing that we are going to do is df.describe. So now I want you to wear your analytical eye and tell me something about vendor ID. First of all, you can see this ID, this first ID is not there. Why? Because this is object. So you cannot find the summary of object except if you impute one parameter. So what can you say? Looking at this, what can you say about vendor ID? Looking at this column. What can you say about vendor ID? Anyone in the chat? Anyone? I'm waiting. Both text and int. Okay. In this vendor ID. So where is the text? In vendor ID here, I can see that my vendor ID is all numerical. Okay, so looking at this, if you look at the minimum vendor ID, is 1. Yes. Ido is saying, I think we're only having 2 vendor category. Yes, thank you, Ido, for that analytical eye. Yes, if you look at this, the minimum is 1. The 25th percentile is also 1. The 50th percentile is 2. 75th percentile is 2. The maximum is 2. Now, this is ringing a bell, meaning we have only 2 categories. That is 1 and 2. So thank you. That is 1. So, but we can closely examine this vendor ID by saying df slash vendor ID does dot what is it value as value counts. So this, I hope, is going to extract exactly. So we can see we have only 2 entries. Those with 2, they're having up to 700,000. And those with 1, they're having 600,000 plus. That's their count. So then, if we know that the vendor ID in this case is only having 2 values, what else can we say about it? Anyone? What else can we say about vendor ID? right, so okay, Abdurrahman is saying it is categorical. Yes, it is categorical. Maybe gender. Well, for in this case, so the vendor is actually the software that is used. Maybe in this case, maybe we can say vendor like Uber and Bolt, for example. So that is standing for the software. So in this case, we may not like another thing that we can say is this vendor ID may not help us in our prediction. So when we come, another action item here is to drop vendor ID because it is not contributing. Then passenger count, okay, in the case of passenger count, interesting. How can you have a ride without passenger? Is that possible? And it is a taxi ride without passenger. So maybe this is referring to the fact that only the driver is in the car and he will bolt himself from one location to the other. So maybe we may exclude readings like this whenever it is 0. So the minimum duration is okay, the minimum number of passenger is 1. Okay, yes, it is possible. And the maximum number of passenger is 9. Maybe we are dealing with we're dealing with sedan or the rest. Okay, we also have the pickup longitude. So in this case, here we can see negative, no problem, because longitude can be negative. We also have the pickup latitude. So this is where any point on Earth can be described using these two numbers. That's the longitude and the latitude. So the first point, the pickup point, is described by the pickup latitude and the pickup longitude. And also in the data set, we also have the drop-off longitude and drop-off latitude. So this is the final destination. Then we also have the trip duration, which in this case is our parameter variable of interest. And then, okay, all this one seems normal. But I want us to zoom into this trip duration. What can we see? Now we are back your analytical eye. What can you say about these trip durations? Okay. Anyone? Remember the duration is in seconds. So what insight can you see? This. Okay, let me do it this way. Okay, now I itemize trip duration. What can you say about this? Can anybody help us? Okay. So looking at this, we can see the minimum is 1 second. How possible to get the trip duration 1 second? You just enter car 1 second and you are there. Maybe it's not possible. So we need to look into this issue when we come to do data cleaning. And also looking at this maximum duration, we can see we have like 3.5 million seconds. All right. So now let's convert this 3.5 million seconds into hours. And we can do that by saying, let me say, open bracket 3.5 times 1,000,000, then divide by what? Divide by, so changing second to hour, we have 60 seconds make 1 minute. So 60 seconds make 1 minute times 60 minutes make 1 hour. So times 60. So this will give us the maximum hour. You can see the maximum hour is 972. Interesting. So 972 hours, how many days is that? So can we convert this to date, to this? Yes, thank you, Kevin, for helping us with that. So converting this to days, maybe we know that in a day we have 24 hours. So we say divide by 24. So, apologies for the mishap. So is it possible to have trip that is, okay, I can see one question there, by Mihiretu. Data, I think from, is it country, right? Moving from, let's say, US to Japan. Right, so having 40 days, that means what? It means there are errors in the data which we need to clean. Okay, so before we do the cleaning, let me answer this question. Thank you. When we work some sensitive data like healthcare, money regulation, and business, we need to learn pattern of data as it and predict for the future, especially in healthcare. By using the actual data, we need the prediction act like it. So in this case, what we need is a model learned deeply. When we do this, the prediction seems actual data. So why we say overfit instead of good fit? Okay, let me try to understand the question again. Like healthcare. By using the actual data, we need the prediction act like it. So in this case, model to learn deeply. Okay, so let me just like try to explain overfitting and underfitting. When we say overfitting, we are not talking about the privacy policy of any data collection like the GDPR and the rest of that. All right. So by you having access to the data, it means the people that are entrusting with the data, the people giving you the job have entrusted you with the data, right? And they also assume you are going to um, use the data, handle the data carefully without exposing the data. All right. So by if that is out of the way, then the data you are given, you may also need to like split it into two. One for training, one for testing. And the reason why you need to split it into two, it may be hard for you to like say you first of all build the model. Then after you build the model, then you deploy it. That's without testing it. You deploy it for people to test. Then you start adjusting. So what we normally do, when we collect our data that is labeled, then we split that data into two. We train the data on one part, the largest part. Then we test the data on the smallest part. Then from there, we can make our life easy. So I hope that answers your question. But if I'm not able to answer the question, please you can ask again. All right. So here we can see that the number of days, there are 40 days, which means something is wrong with this. And this kind of problems do normally come from the GPS itself. So sometimes when the GPS lost signal, then chances are that it may not log off from the duration, from the trip. So maybe a driver that after the first day went on vacation for 40 days before returning, then that will be recorded for him. So we need a way of filtering out these outliers. Like this one is outlier, maximum 40 days is outrageous. Right. So another thing that you can check in your data set is the null values. All right. So how do we check for the null values? Anyone? Or I think we have checked the null values. So we have checked this one. Okay, the duplicates. Yes, it's duplicate that I want to ask. So this is also similar to saying df dot duplicated. Now, when you leave this, it's going to return the data frame. So now we can see all these are false. Now, how do we count any true occurrence in this? So we can say dot sum. So this will return the true occurrences. And now we can see we are having 0 as, so which means there are no duplicates. Now, next, we do what we call feature engineering. What is feature engineering? Looking at this, we can see that when you look at this, where is it, the date? The pick of date is in what? It is an object. So an object A is it. So we need to convert this to date time. That's our pick of. First of all, we need to transform this pick of date to date. So we need to convert date dot Okay. All right, so this is peak update time. All right, so this is peak update time that we want to convert to date time. So how do we do that? We can say PD dot what? Anyone? Can anyone help us? Dot to date time. So what are we going to convert to the date to the date time? Is column to date time. We are overwriting that column with the date time. So we'll do another df.info after we finish the conversion to see what happens. All right. So let's see. First of all, let's do df.info. So you can see this is objects. Now let's convert to date time. Let's run this again. Remember, this is object, so let's run it again. Now we can see this is date time in nanoseconds. All right. So which means we have overwritten the original column in the data sets. All right. So next up, we may need granularity in our data. So what do you mean by granularity? Meaning the date might be something that is too large for us. So we may need something that is smaller. Like we want to, it's just like when you are using microscope to view into your data. So you want to look at the minute points. So first of all, we might want to look up to the last hour or up to the last day, because sometimes maybe the hour can determine the duration. Maybe if there is a lot of traffic, for example, if it is a busy town, there's a lot of traffic. So the hour is important. The day also is important. Maybe you may not expect the traffic during the day, weekdays to be the same as during the weekends, or the months. You may not expect the traffic in December to be the same as the traffic in January or March. So because of that, sometimes we might want to see to the minute time possible. Maybe you can even go as small as second, but for something meaningful, I think you can restrict to the hours. Right. So how do we convert to hours? And to do that, all we need to do is to take what? Is to take the already converted to date time. So now we can extract the hours from it. Then we can say dt dot hour. So this will help us capture the hour. So we can see this is the hours from the time. Now we need to assign this to a new column that we are going to create in our data set. And that new column is going to be called hour. So here to create that, we say df dot, so in this case, we are not overwriting anything. So the new column we are creating is hour. Remember, it's not there in our original data set. So we assign it to this. And when you check your df dot head, here you can see the hour. can see the hour column created. So not only the hour, we might also want to create the day of week. So DF into, I want to call it day of week. Is equal to the same peak of dates, but this time around, we want to get the day of week. Right, so next, we say we want to get the month. All right, so to do that, we can copy this. So here, the same thing, the same month. Now, when we run this, and now we can examine to see that, okay, good. We have the hour, we have the day of week, we have the month. So all these are going to help us in achieving our results. So what next again do we need to do in order to ensure that this is ready for our decision tree analysis? We need to clean the data a lot. So what again? So here we can see two dates, pick up date time and drop up date time. And now here we need to make a decision. And the decision is we are only going to pick one date. Why are we picking only one date? Because if you subtract this from this, you are expected to get this trip duration. So because of that, if you pass the two columns to the model, there is what is going to happen, which we call data leakage. Meaning you are already like given answers to the model even before it do the prediction. So we are only going to use the peak updates. Is that clear? Which means now, first of all, we are going to drop this ID because it is having no predicting power. We're also going to drop this vendor ID because the application should not determine how long the duration is going to take. So we are only going to use pick update. We are going to drop off time. In passenger count, we are going to make use of that. And another transformation that we might do here is calculating the distance. So here we can see the pick up longitude and drop off longitude, pick up latitude and drop off latitude. So we may need to calculate the distance in kilometer. All right, so to do that, there's a formula that you can use to calculate the distance in kilometer for any 2 points on Earth. And this is the formula, right? So how can we model this formula in our work? All right, so this is sine squared theta by 1 minus pi 2 r. So in order to model the formula, there is this function, and the formula is going to take nothing but these 4 coordinates. One is going to take the peak of longitude, the peak of latitude, the drop of longitude, and drop of latitude. So that's the function. It will pick latitude 1, longitude 1, latitude 2, longitude 2. And the aim of this function is to calculate the distance in meters, in kilometers. So R, so this R that you are seeing, that's actually the radius of the Earth. So the radius of the Earth is given as 6,371 kilometers. Now, how do we do the calculation? To do that, so looking at this, we can evaluate this one after the other, then we can keep compiling everything. So first of all, our latitude 1 and longitude 1, latitude 2 and longitude 2, we need to convert them to radians. All right, so we need to convert them to radians. And in converting them to radians, we say latitude 1, longitude 2, we pass them as a list. All right, so this list, then we call np.radians. That will convert them to radians. And that's numpy.radians. Then we do mapping. We map. So the essence of mapping is like this np.radians, you can apply it to, okay, enough of demo. So let me just do it. np.radians. So let's pick typical latitude. Longitude. So we want to calculate the radians of this. So this is the value in radians. Now, if you have a list of these values and you want to calculate their radians for each of the elements, in that case, you can use the map function. So the map will help you to calculate for each individual values, right? So that's why we're having the map here. np.radians. So this np.radians will be used to calculate for this list, this list, this list, and this list. So after we have done that, this is conversion to radians. Then after that, we can now find the difference between the 2 points. So the distance of a given latitude, you can say latitude 1, latitude 2 minus latitude 1. That will give you one of the distance. And we can also say longitude 2 minus longitude 1. That will give you another distance. So after you have done that, coming back to this formula, what else can we do? So this d lat, that is what we got here. We divide it by 2, just as the formula is saying. So this is for the latitude. We divide it by 2. Then that is sine of this. Then we find the cos of this, which is latitude 1 times np dot cos latitude 2. So all this is latitude 1, just like the same thing as this, and this is latitude 2. And then we say multiply by np dot sine longitude. So this is for the longitude, which is longitude 2 minus longitude 1, and that is what we got here. And then we say all power 2. That is all power 2, this sine square, right? So this also similarly applied to this. All right, so after we have gotten this, that is this stage. Next up, we find this square root. So to find the square root, we can say NP dot square root of A, that's of all this. Then after the square root, we find the arc sign. So NP dot arc sign, all multiplied by 2. And this result we multiply by the radius of the arc. So please, if I confuse you, forgive me, but if you don't want the mass, just take the function and make your life easy. So now, having gotten that, we may need to evaluate the distance in kilometer. And to do that, we apply this function that we just created now, give us sign, and we apply it to our peak of latitude and peak of longitude and the rest of that. So applying this, so now we can see our data frame dot head is now having the distance in kilometer. So here we can see the distance in kilometer and the rest of that. All right. So is that okay? Is the computation too much so that I can restrict the computation, or should we go further? Or only if I say, if I reach this level of mastery, I will be the most happiest man alive. Or yes, it's something that you can reach. It's just so, but like here, looking at this, I may need another parameter in order to filter out those outliers, right? And the parameter that I will like us to evaluate is what is the speed. All right, so we can use the speed to filter out all those wrong values or wrong entries. And why am I saying the speed? For example, we know that typical speed of cars, maybe averagely, maybe they go I know mostly, let's say 100 kilometers per hour, or sometimes we can say, for example, if the driver is not overspeeding or is not moving let's say at minimum 40 meters per second. I mean 40 kilometers per hour. As maybe the driver is sluggish in moving. So we can use that to filter out. Then maybe we can say that, okay, all those speeds that are less than some certain point, then they are not valid speed. All those speeds that are more than some certain points, they are also not valid. For example, if we see a speed that is 500 kilometers per hour, I think this is a speed that is reserved for trains and aeroplanes or airplanes, right? So if we see a speed like that, then we can drop that column. Or if we see speed that is 10 kilometers per hour, then we may drop that. So this is another level that we can go, but you have to give me the go ahead. Because as it is now, we can even go ahead and build our model without doing that. But we'll just make assumption. So make a guess and make our life easy. Which one? Let me see your response in the chat so that you will not say I'm overcomplicating the issues. Okay, no response. It means we should just guess and make our life easy. So guessing. So this, we can say df dot trip duration So we want to filter out any trip that is less than, let's say, for example, what is the common duration for a trip? Let's say 5 minutes. So 5 minutes, what is 5 minutes? That's how many seconds make 5 minutes. So we'll say any trip that is greater than 5 minutes should form part of our data set. So what is 5 minutes? To achieve that, we can say 5 multiplied by 60. All right. So when you run this, and what it is doing is it's returning all those trips that are more than 5 minutes. So we can even check, can we check the size of this? Okay, so we can use this to filter out our data frame. So we can say this and this. All right, so what is the length or size of this? Let's see the shape. So you see about 200,000 were shared from our data set, meaning 200 of our data, less than 5 minutes, right? So we're able to filter that out. So what duration do you also think that is too much for a given trip? Should we say 2 hours? I mean, 2 hours or what? So what we can do here, we say our, now we can assign this to our new data frame is equals to this, right? So our new data frame is equals to this. And the second one, we are going to say, so like how many hours is too much? df dot trip so when this is how many hours is too much? Abdullah is saying 4 hours because of Lagos traffic. So let's say 4 hours. So for 4 hours, we can say 4 times 60 times 60. Then I can close this. When I do this, oh, oh, right. So I can now use this to filter my data frame. So all those records that meet this criteria will now form part of my data frame. So my new data frame, I can call it this. So this is our DF. We can say dot dot what, dot shape to see the new size. I think not much. Okay. So now remember, it's not all these features that we are going to use. So we need to select those that are important to us. Maybe one, maybe the pick update is not important because we have already extracted the month, the hour, and the day of week. This one is not important. Passenger count important. So here, instead of picking this, we have already evaluated the distance. So we can use that instead. So here we have passenger count, the pickup hour, or in this case we say hour. Then we have day of week. Day of week. Then which one again? The month. We're interested in that. And we also have the distance in kilometers. Or the distance in kilometers, which is the same thing as this. So with this, we can easily like split our data sets. So we can find our X and Y. And from this, I think is something that you are very familiar with. We can do our trend test splits. Then we can initialize our decision tree model. And here we are saying the maximum depth should be 10, meaning the number of leaps should be up to 10. You can choose any number. So maybe we can choose 8. Minimum sample splits, meaning the minimum sample for a given level should be 10. Maybe the random number should be 4. And after that, after we initialize, we can now make predictions. After making predictions, we can evaluate this model, or we can train the model. So this is training. Then next we can make prediction. Then after making prediction, we can then evaluate the model, finding the RMSC and the R2 score. So here we can see the RMSC is 380 seconds. The R2 score is 0.66, meaning 60% of the variation we are seeing in our data sets is actually explained by this model. Nice try. Then can we make this model better? Yes. So how can we make it better? So in order to save our time, all these steps, I've already captured them in this function. So this is going to do training the model and making the prediction. I'm also making the evaluation so that we just pass the model and the data, and the model is going to regurgitate these values. And we are going to apply this in order, to test our ensemble method. Remember, we say that the ensemble methods are going to be better than the single method. So if you have one model, maybe you have 10 models, so the 10 models are expected to be more than or perform better than that. So going to ensemble method, here we have, one of them is called the random forest. So, in a forest, you have a lot of trees. So in this random forest, you have a lot of decision trees that are coming together to give you that. So first of all, we instantiate the random forest regressor. And here we are saying the number of estimators, they are 100, meaning in this forest, you have 100 trees that are coming together and joining forces in order to make the prediction. The maximum depth should be 5. Okay. Let me check what depth did we use here. We use 8. Okay, so let's use 5 here and see what happens. So after initializing this, we can now call this function that we create to just make our life easy. So let's see whether that will happen. And so this will take time. So you expect the work that is going to be done by 1 is now carried out by 10 people, and all of them are doing it together. So it's going to take time. Then here is also another one called debugging. Then we also have the other boosts. When you get the note, you also have the stacking and you have the voting. Right? So this is also taking time. Now, as it is taking time, let me run this, and this. Then this, and this. This is still taking time. While it is taking time, okay. Let me see if you have any questions. Okay, I can't see any questions. So for the Q&A, okay, please, the poll can be launched. So while the poll is being launched, we will. Okay, somebody is asking. Yes, I'm going to definitely. We are sharing the notebook. So as the poll is going on, hopefully by then, maybe before the end of the webinar, this will finish. Remember, this is up to like 1.2 million, and we are doing it like 10 times, so it is going to take time. So as that is happening, I'll hand it over to Najoli to close out. And hopefully we'll be able to see one of these things. Even this one, to see whether it is better than random forest. I mean, decision tree. So this is random forest. We're hoping it will be better than decision tree. All right. Over to you, Najoli.
Okay, thank you for that, Buhari. Thank you for that amazing session that you've held for C9, even as we are walking into this. Let's continue feeling the poll even as we get to the very tail end of this, even as we get to close this. Some announcements that we have at hand are as follows. That first of all, yes, the previous slide, please, Buhari. Yes, if you have any questions, any issues, matters, the community space, matters, your program or content related questions, kindly drop them at the Ask Data Programs teams channel on eHub. If you have any technical issues, before you drop them, right at the ALX Data Programs team channel, kindly drop them at the Fresh Desk so that we can be able to just have a ticket for that. And finally, if you have any technical issues, matters the code challenge that you'll be submitting, kindly submit them on AnswerBase, and our technical mentors will definitely be there to get to answer your specific questions. Our next steps are as follows. We have the decision tree code challenge that is due next week on 30th March. Quite the journey to just get to see how far we are diving deep into this, even as we are having this in mind. Find our session recordings and resources on the Programs Hub space on eHub. And finally, as always, remember you're not alone in the community. Engage in your squads, ask for clarity, post your wins, challenges, and new insight on your squads spaces, even as we head to the tail end and conclusion of this. See you next week. Ensure you've asked your friends to activate who've not begun their content yet. And yes, enjoy the rest of your weekend. The rest of your week, sorry. Yes. You can listen to this song even as we'll be heading out. I'm not hearing a song. I think we should be singing even as we are closing this. What are you singing for us?
All right. I think maybe maybe it has consumed the data, and up to now it's not yet
Uh,
finished. So please, when you get it, you can actually make your life easier.
I'm not hearing the sound, Buhari, on my side. I'm not sure whether it's just me.
Listen.